All right, today we're going to talk about centripetal acceleration. So we've been talking about circular motion. Essentially, how does an angle change over time? We call that angular velocity, or how does angular velocity change over time, or angular acceleration. Then we also looked at how the changes in the angles over time, angular velocity, how that would determine tangential velocity. So for instance, like if we knew let's say we have this ball on a string and we're spinning it around in this clockwise motion. If I let it go at this point, what would be its tangential velocity? That would be essentially what direction is it going to go, once I let go. So looking at it at this point, I know that, as I'm spinning it around, let's say I'm not going to let it go, it still has a tangential velocity that's kind of straight out this way. It's tangential, or it's a tangent to the circle. Let's pretend that's a circle. Uh, Fix that quick. All right, so yeah, it would just go straight that way, or at any point, once it's at this point, its velocity is still forward. Well, we know that that velocity can't change even in direction unless there's an acceleration. So we're going to call that centripetal acceleration. What we're going to find here, like if the ball's on a string, what's providing that acceleration is going to be the string. That string is constantly pulling that ball towards the middle. So essentially, like if I do kind of my head to tail thing, so if velocity is that way and I accelerate it that way, that means my new velocity will be in that direction. So then if I'm going that way and we're getting accelerated towards the middle, essentially we keep doing this um, to keep figuring out, what direction is this thing going. Ignore that one. So centripetal acceleration, really my whole big takeaway here is it's the acceleration of an object towards the middle of a curved path. Sometimes that's being applied, you know, by the inside, it's being pulled towards the inside like a ball on a string, yo-yo on a string, anything like that. Or, this is the reason why they bank curved roads is they want that centripetal acceleration. They want to accelerate people towards the inside of a road. So that, with that case, the centripetal acceleration is still there, it's still toward the middle of a curved path, but it's being applied from kind of outside the circle, if you will. All right, so let me go back and talk about. Oh, we can do better than that. Let's talk about the ball. Whoa. Okay. Um, Ignore that for now. So this ball here, let's say that it has a certain amount of tangential velocity, and we want to know what the centripetal acceleration is. And it's at some distance r from the middle. The way that we're going to find centripetal acceleration is that's really going to be equal to the tangential velocity squared divided by the radius it's moving in. So let's do some unit analysis here. Okay, so we know acceleration, we're looking for meters per second squared because centripetal acceleration will be the same as that kind of translational acceleration we worked with earlier in the course. Velocity is meters per second, but in this case, we're going to square that and we're dividing it by radius, which is still m. Let's go ahead and put that squared with both of these. So we have meters squared over seconds squared all over meters. So in this case, that meter is just going to cancel out that square there, and we're left with meters per second squared. All right, and that is what acceleration's in. So if that's acceleration, this is centripetal acceleration. So even though we're kind of going about a different way, we're still getting the same unit. We're still finding acceleration. So let's go back to ball on a string. Let's say that we're whipping that thing around, so like it's tangential velocity. So let's say we want to know what the centripetal acceleration is here. If let's say that the radius of the string that we're kind of spinning this ball on, let's say that's 0.8 meters, okay? And let's say, so we'll go r equals 0.8 meters. And let's say that the we went through, we figured out the angular velocity, took that times r, and we figured out that the tangential velocity is, let's go with 5 meters per second. All right, and we want to know what's the centripetal acceleration. So in this case, I'm going to come up here. Centripetal acceleration is equal to that tangential velocity squared over the radius. Tangential velocity we said was 5 meters per second. All over the radius we said was 0.8 squared over 0.8 meters. Okay, so in this case, 5 squared is we got 25 meters squared per second squared all over 0.8 meters. We just went through that. Meters cancels the squared. That math, however, I can't do in my head. Bring up the calculator. So we've got 25 divided by 0.8. So we're looking at 31.25. Where we go? Okay. Meters per second squared. All right, so that's how much this ball is being accelerated towards the middle. And keep in mind, this isn't changing like the value for the velocity. Like the speed of the ball isn't changing. It's pretty constant. But since we're changing the direction of that velocity, there has to be an acceleration there. And if we want to be more specific, we would say the centripetal acceleration is 31.25 meters per second squared towards the middle of the curved path. All right, so one more thing we're going to add to this. So let's say let's look at same thing. So ball on a string. And it kind of cuts out a curved path here. If I'm diagramming this out, and we're going to say it's going that way. This time we're going to use a smaller string. We're going to say that has a radius of 0.3 meters. And we're going to say that we measured the tangential velocity. We're going to say that we're going slower, way slower, 2.3 meters per second. And we're going to say that our ball here has a mass of 1.3 kilograms. This thing's got quite a bit of mass to it. Well, just like if we knew, we could find force was equal to mass times acceleration, we can find centripetal force if we take mass times centripetal acceleration. Or since I know centripetal acceleration is equal to tangential velocity squared over r, I can plug this into here and I can find that centripetal force is equal to mass times the tangential velocity squared over r. This will get us to newtons as well, or kilograms meters per second squared. All right, so over here, let's say I want to know what's the centripetal force that the string is pulling on the ball with. Okay, so in this case, they don't give us straight up centripetal acceleration, but they give us the tools so that we can find it. So the mass we said was 1.3 kilograms. Vt, the tangential velocity, we said was 2.3 meters per second, but I do need to square that. That's over the radius we said was 0.3 meters. All right, I have everything I need. I just need to plug these numbers in. So let's go ahead and bring this back over. So I have 1.3. That's my kilograms times 2.3 squared divided by 0.3. Looks like we're going to have a centripetal force of 22.9 newtons. Or 22.9 kilograms meters per second squared. And keep in mind, if I'm looking for a radius, let's say I know the centripetal force, the mass, and the tangential velocity. If I'm looking for r, I would just multiply both sides by r, divide both sides by centripetal force. I would find that the radius is equal to mass tangential velocity squared divided by centripetal force. So essentially, we can do algebra to these things. We can substitute equations in for things and still be fine. Like, for instance, if I didn't know the tangential velocity, I could plug in tangential velocity is equal to radius times the angular velocity. I could plug that in for VT if I knew the radius and the tangential velocity. Anyway, that's kind of centripetal acceleration, centripetal force. Uh, Looking at, if we have a velocity, that has to be caused by an acceleration. We have an acceleration that needs to be caused by a force, and this kind of, brings us full circle, if you will. Pun intended. So with that, good luck with the practice.